welcome back to episode 2, part 2 of explaining physics concepts. And in this video, we will be looking at gravitational fields and the three remaining parts of it: geostationary object, gravitational potential, and past paper questions. In our last video, we looked at the Newton's law of gravitation, the Kepler's law of gravitation, how gravitational force is related to centripetal force, and all of that. And now these three very simple topics are remaining, and we will be done with this entire chapter. So starting off with geostationary object. Geostationary object is, I would say, a very small part of this chapter, and there are just a few points that you can learn, and that will be it, honestly. And it's related to communication, and I'll just quickly type down the points that you must learn, and that is literally what past paper questions, as far as I've seen, that's what they usually ask. So let me just quickly type them down. Number one, geostationary object is, it's there's an object that is just moving around in this geostationary orbit. It remains at the same point above the Earth's surface. Number one. Number two, it has an orbital period of 24 hours. It has an orbital period of 24 hours. Number third, it orbits from west to east. It orbits from west to east. And fourth is, it is directly above the equator. And these are just 4 points that you can just know about geostationary object. These are the characteristics, and honestly, that is it. Now, before we move on towards our a more important topic, gravitational potential, there is a very small minor thing that is written in the syllabus, that is small changes in height. So for that, I will draw a graph. Now at this point, this is R, this is R, this is, and outside the Earth. And this right here is G. Okay, so for small changes in height, what it says, if there is a very small distance, a very insignificant distance in comparison to the radius, then the G remains relatively constant. Let's assume I have a planet here, and the radius is, let's say, 10, but the distance that it's to travel, that is only 1. Since there is an insignificant distance compared to the radius of the planet, the G remains relatively constant, which means if this is the radius, if this is like the radius, and if there's a very small, and for still this radius, if there's a very small distance, the G here, it will remain constant to only 9.81. That is literally it about this entire concept, that if the distance it's very small in comparison to the radius, then the G will remain relatively constant. And it's an added point. How did we derive this? How did we derive this relationship between G and R? How did we come up with this graph and all? Let me explain it to you. Earlier, we talked about gravitational force, that was GMM over R squared. And then we also had F is equals to mg, ma, so we have G is equals to F over M, right? Now, if we relate both F, you can have GMM over r square equals mg. And simply when you cut m, you have gm over r square equals g. Now, since gm is constant, I can just have 1 over r square. Look at this. This shows that g and r square, this is the relationship we found between g and r square, which shows as the distance increases, since they're inversely proportional, as the distance increases, g becomes insignificant. The entire point was, always remember, this r is not just the radius, it is the distance between the two planets, and their radius is not just the radius. So what the entire purpose was, that if the distance is too small, g is constant. But in this relation, we can say that if this distance keeps on increasing, then yes, it won't remain constant, it will just start decreasing, it will become insignificant and can go to infinity, which is shown right here. That as outside the earth, as the distance keeps on increasing, the g will start decreasing and it can even go to infinity. But as long as it is smaller than the radius, it is insignificant compared to the radius, then g will remain constant. But the moment it goes out of that radius, the distance starts increasing, g starts decreasing. And that is it. Now we're going to move towards gravitational potential. Now let me just quickly write what gravitational potential definition is, and then I'll explain it to you. Gravitational potential, I'll denote it with GP. Gravitational potential at a point is the work done by unit mass in bringing a small test mass from infinity to the point. Now, let's assume there is Earth, and at infinity, let's assume this is infinity, and then there's a very small test mass. The energy, since this is where the gravitational field is, since we have to move it towards this from infinity to this point, the work that is required, the energy that is required per this mass is called gravitational potential. And the formula for that is phi equals minus gm over r. I will tell you why it's minus. There are whole explanations for it, and these are even usually asked in the paper as well. So minus gm over r. But if you want to find gravitational potential energy, all you have to do is multiply this with m, and you will get minus gm m over r. So you got two formulas, minus gm over r for the gravitational potential, and minus gmm over r for gravitational potential energy. Now the question arises, why is gravitational potential negative? Okay. Why is gravitational potential negative? Number one, gravitational forces, there are just 3 points that you can learn, and I will explain them to you so it will automatically just sit in your brain. Number one, gravitational forces are always attractive in nature. gravitational forces are always attractive in nature. Number 2, we assume that gravitational potential at infinity equals 0. We assume that gravitational potential at infinity equals 0. Number 3, when we move in the direction of the gravitational field, when we move in the direction of gravitational field, we lose gravitational potential energy, which means it gets negative because work gets out. Let me explain all of this to you. Now let me explain all these 3 points with the help of a diagram. Let's assume I have a planet here, Earth, let's say, and there is a small test mass. This is infinity, and when this is infinity, we are assuming that at infinity the gravitational potential is equals to 0. Now the test mass that has to go from here to the center, number 1, since the gravitational forces are always attractive in nature, so it will automatically pull it towards itself because it's attractive in nature. Number 1 point, when they're attractive in nature, it's bound to move towards this. Now when we are assuming it's at 0, infinity, it's at 0, and since we're moving in the direction of the gravitational field, we are losing gravitational potential energy, which means we are becoming negative. Why? We know one thing for sure, that these two are attractive in nature, so it will automatically start moving towards this. But work has to be done to pull them apart so it can stay at infinity, so we can just keep them apart. And while doing so, the work that is required to keep them apart, work is done and it gets negative. Work gets out, which means the energy that's required to keep them apart, it just gets negative, because it's like you have 0 here, and then it's going in a backward number line, -1, -2, -3, -4. So this is the planet at infinity, and then it just starts moving that, because gravitational forces are attractive in nature, and so we have to need energy to pull them apart, and that is why it gets negative. I hope that was clear and that made some sense. Now moving on towards another part of this chapter, that is energies of a satellite. Because ideally what we do is that we have to sort of keep two planets from getting attracted to each other. We have to pull them back, we have to push them back to infinity, and so in doing so we need some work, and we need to do some work. Now when we talk about energies, there are just 3 energies that are revolving around in the satellites and etc. That is, number 1, the gravitational potential energy. Then we have the kinetic energy, and then we have the total energy. Now we know what gravitational potential energy is. We have minus G m over r. Now what do we know about kinetic energy? There's one formula we know, that is 1 over 2 mv square. Where do we get V now? Okay, in our last video we looked at how gravitational force is related to centripetal force, because gravitational force is providing the centripetal force. So we said, how about gmm over r square, we need to find v, is equals to mv square upon r. This is the formula of centripetal force. This is the formula of Newton's law of gravitation. We cut m out. This r gets cut as well. So we are left with gm over r v square. We know what v square is. Gm over r. I just replace this and I get gmm over 2r. That is my kinetic energy. Now what do we mean by total energy? Total, obviously it's the sum of these two. So I can just say minus gmm over r plus gmm over 2r. Since this is, we have to make the denominator same, 2 minus 2 gmm plus gmm over 2r, and you get minus gmm over 2r, and this is your total energy. I took LCM, I got 2 here, and that is it. Now if I were to plot these in graph, you could see obviously as you're moving towards a planet, your kinetic energy it decreases because your gravitational potential energy it increases negatively, because we just said it's negative, so gravitational energy increases, and then here we have the total energy. So this is kinetic energy, this is potential energy, and this is total energy. Total energy, potential energy, and kinetic energy. Okay, now we're done with total energy, we're done with all of that. There's just a very little portion that is left, that is called sensation of weight. Now the sensation of weight is when you're sitting, you feel that your weight is down because your weight is like acting in the downward direction. Why is that? Because that is because of a force called normal reaction. Let me explain. You have a planet here and you have an object sitting. Now there is a force, obviously whenever there's an object sitting on a flat surface or anything, if there's a force acting down, we know that's gravitational force. Obviously there's a force that will be acting up, that is normal reaction force, right? That is going to be written as reaction force, right? Fr and Fg. Now if it's in this direction, if this is in the direction, if we subtract these two, because we have to find the resultant force, Fg minus Fi, you get what? The centripetal force, because centripetal force is the resultant force, so Fc. So I can just say Fg is gmm over r squared. Fr is what? Sensation of weight, right? And what's our weight? Mg equals centripetal force. And in most cases this is sometimes so insignificant we can even ignore this, and we can just say gmm over r square is equals to the centripetal force. That was the entire point. That the reason why when we say sensation of weight, we mean the reaction force, because there is this gravitational force acting in the downward direction, and in that very opposite direction we have the normal reaction force, and then when we subtract them we get the centripetal force, and that's it. And now we're going to move towards one practice question. I will share the year here, past paper year, that is summer 19. Let me just write it down. Hey, June 2019, 4-1, and question number 1. And it says, Two point masses are isolated in space and are separated by a distance x. State an expression relating the gravitational force F between two masses to the magnitude m and m of the masses. Okay, we have F, we have m, and x. We can just put them together and find the gravitational force. We know F is gmm over r square, but we have to adapt to what the question is saying, and we have to write g m over x square. And they're also saying state the name of any other symbol used, so where we can say where g is the gravitational constant. And then B part, a spacecraft is to be put into a circular orbit about a spherical planet. The planet may be considered to be isolated in space. The mass of the planet assumed to be concentrated at its center is 7.5. So we have a spacecraft and we have a planet. And so we have a planet and then we have a spacecraft that has to orbit around this. Now the mass of the planet mass is 7.5 into 10 raised to the power 23 kg. The radius of the planet is 3.4 into 10 raised to the power 6 meter. The spacecraft, and the first part says the spacecraft is to orbit the planet at a height of 2.4 into 10 raised to the power 5. Spacecraft height is 2.4 into 10 raised to the power 5 meter above the surface of the planet. At this altitude there is no atmosphere. Show that speed of this spacecraft is 3 point, which we have to prove. Now, one thing that should instantly pop up in your mind is speed, which means we have to use the kinetic energy formula, right? And we know what the formula for the kinetic energy is. Not even kinetic energy, essentially it is the speed formula. We just write that, and that was v square over gmm. V square equals gm over x, right? Now v square we have to find. G is 6.67 into 10 raised to the power minus 11 multiplied by mass, which is given to us as 7.5 into 10 raised by 23 over x. Now what is x? I told you r/x, it's not the radius, it's the distance plus the radius, which means if I have the radius, if this is the radius and this is the distance, right? They have given us the height. We have to add all of this to get x. So the x is 3.4 into 10 raised to the power 6 plus 2.4 into 10 raised to the power 5. And when you multiply and use the divide and all of that, you get 3.7 into 10 raised to the power 3. 3.7 into 10 raised to the power 3 meter per second. Now, the second part says, one possible path of the spacecraft is shown in figure 1.1, and if figure 1.1 is technically, we have a planet, and this is point A, point B, this distance, and then we have this distance, 5 into 10 raised to the power 7, 3.64 into 10 raised to the power 6, and then we planet. At point B, the spacecraft a distance of 5 into 10 h per 7 from the center of the planet. The spacecraft has a spacecraft velocity at point B is 4.1 into 10 raised to the power 3. The mass of the spacecraft is 650 kg. For the spacecraft moving from point B to point A, so it's moving from point B to point A. Show that the change in gravitational potential energy. So we have to find the gravitational potential energy. Simply, all you have to do is find the gravitational. Since we have to find the change, find the gravitational potential energy at this point. Find the gravitational potential energy at this point. Subtract them. You'll get the answer. Now, what do we have? Gravitational potential energy at point B. Gravitational potential energy is minus gmm over r. You can ignore minus sign for now because we're just finding change and we do not need to include this minus sign. And then you have minus gmm over x, sorry. And for point B, you have G, and then you have the mass 650, and then you have the mass of the planet as well, which is 7.5 into 10 raised by 23 over x. You know what the distance is? That is 3.5 into 10 raised to the power at B, 5 times per 7, and you just have to subtract this from the one that is at A. 650, again the same values, over 3.64 into 10 raised to the power 6. You subtract them, you have to prove that you get 8.3. That's it. Whenever you see the word change, subtract them. And now the C part, by considering changes in gravitational potential energy and in kinetic energy of the spacecraft, determine whether the total energy of the spacecraft increases. Okay, so we have to look at the kinetic energy plus the gravitational potential energy to see what happens with the total energy. So we have to use these two both to define what happens to this. Now, what's the formula for kinetic energy? Minus gmm over 2r. And what happens to the gravitational? What's the formula for gravitational potential energy? Minus gmm over r. Now, if you could say from B to A, the distance x, it decreases. Now, if you look at this formula and you go, oh, if the distance decreases, since they are inversely proportional, the kinetic energy should increase, and the same goes for this, and so the total energy should increase as well. Let me tell you a very basic and a very frequent confusion that I faced as a student, and that was the signs. These signs messed up a lot of things. If you were to look at this, and you would have gone minus gmm over 2r, and you would have seen, ignoring the negative sign, that if this decreases, this increases, if this increases, this decreases, because they are inversely related. However, here it has to be opposite. We can see from B to A, R, it decreases, right? It's going from 5 into 10 raised to the power 7 to 3.64 into 10 raised per 6, so it's definitely decreasing. When R is decreasing, the kinetic energy will also decrease. Why are we saying that? I'm saying, let me give you an example through numericals. I'm saying, initially, let's say the kinetic energy at B, the answer that I get was minus 20. And then when it goes to A, it becomes minus 70. Now, minus 20 minus 70. Minus 70 is less than minus 20. It's decreasing. Kinetic energy is decreasing. However, but the magnitude is increasing. That is why we form that relationship. I hope this is making sense because it's extremely important. When I said at B, when the radius was greater, kinetic energy should be less. And at A, when radius was less, the kinetic energy should be greater. However, the kinetic energy is decreasing. The magnitude has increased, but overall it has decreased because of this negative sign. And we know in math and negative signs, we say that minus 70 is less than minus 20. So we are saying whenever you see a negative sign, even if there is an inverse relation, you make that a direct relation. So in this case, the answer to this is that since both kinetic energy and potential energy decreases, because number one, the radius is decreasing. So when the radius is decreasing, as you can see, there is a negative sign in both of them. So whatever happens to radius, it happens to kinetic energy and gravitational energy as well. So in both kinetic energy and potential energy decreases, the total energy also decreases. That's it. Don't go into many explanations. You just have to see the relation that if whatever happens to potential energy and kinetic energy, you'll get 1 mark for that, for identifying what happens to kinetic energy and potential energy, and then 1 mark for what happens to the total energy. And this is it for this entire chapter. I hope it helps.